asteroids, everything closer than we are normally talking about as astrophysicists. Yeah, received already many prizes. An asteroid is named after it. And so today he will talk about the Asteroid Day and results we can achieve the telescope. So please.
Thank you. So welcome everybody. Today we are just celebrating that the asteroid meets again. So we are all here. And in particular, this Asteroid Day Barcelona tries to, popularize this recent progress with different instruments that have been used essentially to study asteroids. In particular, I will announce that the Observatory del Montsec, aquí a Sant Esteve de la Farga de Lleida, Catalonia, just has joined the International Asteroid Warning Network that, in fact, has been for almost 2 decades contributing to the study of near-Earth asteroids, and with particular duties in the follow-up and quick tracking of potentially hazardous asteroids. So this is big news, and we thank the International Asteroid Warning Network for this recent incorporation of the telescope Joan Oró in this category of high-rank observatories. So just to start, well, I will just include in this slide in 2 scales. We can see here small bodies in the solar system, bodies that are tens of kilometers in diameter, like particularly these bodies has been observed from nearby by space missions. We can get high resolution images, here not so big, but just to keep the different scale. You see here, for example, comets. You see Lutetia, that was the first body overflew by Rosetta mission before going to the comet Gerasimenko. And then other space missions that were just obtaining images of relatively small asteroids, less than 100 kilometers in diameter, that are the most common asteroids in the solar system, most of them directly in the main asteroid belt that is among the orbits of Mars and Jupiter. Lutetia is in the other scale. We are going to see here Vesta, that is about 500 kilometers, is the second asteroid in diameter. The largest one is Ceres, that is in the size of a small planet, in fact. And it's in the category of planetary bodies because Ceres has, in fact, about 1,000 kilometers in diameter. That is the diameter with the typical rock-ice ratios we observe in the rest of the bodies, in which we expect for a body of about 1,000 kilometers in diameter, full differentiation in the different layers with the core, the mantle, and the crust for Vesta, for Ceres. In the case of Vesta, that is relatively smaller in comparison, we expect perhaps that the differentiation is early stage in which the body is so big that it's unable to release all the energy that has been accumulated for impacts, for large impacts in the first ages of the evolution of the solar system, but also by the solar-like nuclides that went incorporated into the body. So if these bodies are big enough and dense enough, most of this energy is not released to space, as happened in highly porous bodies that are about less than 300 kilometers in diameter. This is the case in here. And as consequence, you have, for large bodies, differentiation, melting of the interiors. The rest that are not differentiated, these are pristine objects at some extent, because in fact, most of these bodies, as we can see here, are tortured by impacts. Some of them were catastrophic, in fact, were completely fragmenting these bodies and making them very different to the largest asteroid series, Vesta, that are almost spherical in shape. And that's the history that is behind of all these bodies. Obviously, when we talk about asteroids, we talk about a pleiade of very different objects in shape, in density, in structure. In a structure is another thing. Could be completely different the structure, very solid and differentiated of a large asteroid compared with a rubble pile that is just the result of catastrophic impacts and then piling again as consequence of the self-gravity of all together coming back to the center of gravity of this asteroid. So, of course, in consequence, to deflect asteroids in a wide range of properties and sizes is a big challenge requiring international cooperation. And I will give some examples in the talk. We can see here the accumulated number of asteroids. We see that nowadays we know a bit more than 1 million asteroids. Here we have Sirius, here Vesta, and the rest of asteroids. When we are going to diameters of 1 kilometer, 100 meters, we increase the numbers, the expected numbers, in tens, hundreds of millions. But of course, thanks to these new surveys, we can go and discover many millions of asteroids that still remain to be discovered, for example, in the main asteroid belt, but also in other regions of the solar system. So the word asteroid is saying us that these bodies look similar to stars. In fact, they are stars through our telescopes, just points of light that are moving across the stars. And this movement, lucky of us that we discover photography first and now digital cameras that are highly sensitive, and they are able to track the movement of these asteroids through the stars. Of course, many of these asteroids, we cannot see them because they are so small and they are just reflecting a very small percent of the light coming from the sun. Ordinary chondrite type of asteroid could be more or less having an albedo of about 10%. 10% of the light is reflected in the surface, and then the luminosity of the object is not so big due to this process. In the case of carbonaceous chondrites, for example, bodies that are more opaque, just the albedo can be of only 3–4%. So these are very difficult to be discovered. But in general, we have three main classes: rocky, and in rocky we have chondritic and achondritic, so undifferentiated or differentiated rocks. Rocky irons that are a mixture between iron meteorites and rocks, and the pallasites we have in the collection is a good example of that. And iron meteorites that are basically iron nickel alloys that are coming from the interior of planetary bodies that no longer exist. These meteorites reach the Earth as irons because these planetary bodies were disrupted a long time ago in the origin of the solar system. In fact, thanks to Hayabusa mission of the Japanese Space Agency, we have really precise images of Itokawa. That is the scale of 100 meters. We see that they are boulders, big blocks, big chunks of rock on Itokawa that can be of the size of a football field. So it's really an example of many of these asteroids approaching to the Earth are rubble piles. It's the Itokawa, one of the best examples. Continuously, we are receiving a flux of fragments of asteroids. Some of them are micron size, produce micrometeors. We can see even through the telescopes some of these micrometeors. But at naked eye, every night, we can see also meteors, or if they are brighter than Venus, fireballs. This is consequence of this continuous erosion of the surfaces of minor bodies that have relatively small gravitational field. So if they get an impact by another body, it's relatively easy that some fragments can be thrown away and then remain surrounding the sun over time scales of few millions of years, depending on the size. 1 centimeter particle released at the location of the main belt, it can take about 100,000 years to little by little decay in the orbit until falling against the sun. So these are the time scales in which really small particles throw away a little bit from this main belt and form the cloud of particles that we call zodiacal cloud. Among the millions of asteroids that are in the main belt, about now 2 million bigger than 1 kilometer, these asteroids can get orbits, I will explain it in the next slide, that are crossing the region where the Earth, our planet, is. Until June 17th of this year, we know 873 with diameter larger than 1 kilometer and about 59,000 in total, with about 121 comets. Among this population of objects that are crossing the orbit of the Earth, we distinguish a subgroup of potentially hazardous asteroids with a minimum intersection orbit, distance of intersection with the orbit of the Earth, less than 7.5 millions of kilometers, and that at least have 150 meters. In this subgroup, we identified so far 152 of larger than 1 kilometer and about 2,500 in total nowadays. About 90% of these bodies, near-Earth asteroids or potentially hazardous asteroids, are coming from the main belt. And then there are other bodies coming from outwards, from regions far away from this. In this graph, we can see basically this is the semi-major axis of the orbit, but we can basically explain this as the distance to the sun. Sun will be here, the Earth that defines the inclination of the orbits of the rest of the bodies in the solar system to be in here at 1 astronomical unit and 0 degrees. And you can see here the different populations with different eccentricities. Athens, Apollo, and Amor are the 3 more important ones. And in the region where Mars and Jupiter are located, between them, we can see these green points that are making this cloud. That is the main asteroid belt, characterized by relatively low eccentricity, low inclination orbits. But this region, as you see here, with these almost forbidden regions in the dynamic movement of the asteroids, we can find main resonances with different planets. They are some of these resonances that are associated close by of Mars, with Mars, this one with Jupiter. One revolution of an asteroid in this location makes the asteroid at the 3rd revolution finding Jupiter. So Jupiter will be removing this asteroid relatively quickly as effect of the gravitational field of the giant planet. In fact, Jupiter and also the secular resonances of Saturn are playing a role in the in eroding in these particular regions the distribution of asteroids. The asteroids are removed by Mars, by Jupiter and Saturn, mostly producing these populations of minor bodies in the near-Earth region. In general, the asteroids that are coming from the main belt remain in this area few millions of years, and then dynamically they are finding the way to get back to the main belt. So no is the case that most of them are just hitting the Earth or the Moon or other planets. If not, in general, this steady state population is coming back to the main belt and keep playing for ages. And in this graph, we can see also this Jupiter family comet population. We know very little, and we hope to learn many more. These are typically fragments, comets or fragments of comets, really dark population of objects. So we know relatively a small number, but they can find also the way to become asteroids. It's about 10% perhaps of the population of NEOs are produced from this more remote population of eccentric comets of the Jupiter family comet. And we are observing this continuously. And we are lucky to have this project in which we are studying fireballs. We detect fireballs every night, and we can explain the fireball phenomena. Over Spain for 30, 40 years, no one has been talking anymore about UFOs because every phenomenon coming from the sky is well explained. We recovered this, in some cases, meteorites from these fireballs, but we have made over time that this is a citizen science project in the Institute, in which we are having about 60 decided amateurs contributing almost every day with detections, things that allow us to monitor the entire sky over the Iberian Peninsula, over the Canary Island, also in cooperation with other professional observatories. And then we can get, you see, these are detections made yesterday of bright bolides. This one from Valencia, this one over Aragon, Catalonia. So in general, we can give the different detections, we can study the origin of these bolides, and we can obtain the orbits. Of course, you will remember probably this super bolide we had last year in May 18, 2024. That it was a really amazing bolide crossing Andalusia, Extremadura, and going and finishing over Portugal. This was a bolide also recorded from space. You can see here the detection and the total radiated energy, 3.7 to 10 to 10 joules, or about 0.13 kilotons. And these were some of the amazing. We got more than 20 detections from our stations. And in addition, we incorporate this amazing detection from Casas de Millán, from the European Space Agency, All Sky 7 network. But these are examples of some of our collaborators: Antonio Robles from Stepan Sevilla, from Navianos de Valverde in Zamora, Miguel Ángel Furones, or from Sanlúcar de Barrameda, Cádiz, Miguel Andrés García, with these amazing recordings. We reconstruct the trajectory, the really unusual, extremely long trajectory of the bolide that allow us, in fact, to obtain details about this amazing bolide, the velocity, the density of the body, and the origin of the body. In particular, this bolide was quite unique because, in fact, we can say that we observed the fall of a comet. It was in the very limit of 1 meter size that, according to the IAU, is recognized as a comet. So we had a meteoroid that was almost 90 centimeters in diameter. It's in the limit of a comet that was crossing entirely the Iberian Peninsula. And for the very first time, the orbit we obtained from ground-based observations and from satellite data, and taking into account the dynamics, the orbit, and how the orbit evolves in the solar system, for the very first time, and we published in monthly notices of the Royal Astronomical Society, we demonstrate that came from a Jupiter family comet. So this is really exciting. We can see here the comparison between the two orbits, one derived from ground-based observations and the other from satellite data. Are not exactly identical, and here are the small discrepancies found in the. It's always a challenge, because of course you need to obtain the orbit from a body that is ablating in the atmosphere for a few seconds. So it's now or never. And here is the example with the different orbits. This was published in Peña Asensio 2024, monthly notice of the Royal Astronomical Society, and you can see here, in comparison with hundreds of bolides detected by networks, the peculiarities of this orbit that allow us to explain that probably the progenitor of this large chunk of comet was the disruption of a kind of Sungracer comet that released this fragment until last year, May 18, crossed the entire Iberian Peninsula. But the news were at the beginning of this year full of one asteroid that in fact was discovered a few days after the close approach with the Earth. Remember, Chelyabinsk in 2013 was hitting the atmosphere over Chelyabinsk, over Russia, just getting it unnoticed by any type of network, or even in the case of telescope networks. But because from the ground, still we have some regions of the sky, particularly close with that geometry, with that incoming geometry close to the sun, in which some of these asteroids can get unnoticed, and then we can have detections few days after the close approach. In a difference of what could have happened about 10 years ago with the Chelyabinsk or with Duende, remember Duende was coming the very first day, was an asteroid, bigger asteroid, that was really approaching on the very first day in which Chelyabinsk was happening. Many of us think that was not casual. Probably we can have some clues there of something that happened in the past, some close approach of a rubble pile, perhaps disrupting in pieces and coming the very first day. But in general, we can keep studying this process. After that event, and with the protocol that has been developed with COPUOS and the ONU, the protocol means that when we discover an asteroid that is larger than, is estimated to be larger than 10 meters, and the probability of impact in the future is estimated to be larger than 1%, then automatically the protocol is activated, and then a global call for new observations is made. That was the procedure for this 2024 R4, in which Basically, in few weeks, we got enough number of astrometrical observations to improve the orbit and to little by little rule out the impact with the Earth. What was really important, and many times is a good example of why investing in really big infrastructure in space makes sense. Thanks to the observations of Hubble Space Telescope, and particularly with James Webb Space Telescope of this asteroid, the accuracy of the orbit was improved few months after the discovery, allowing us to be completely sure now that won't be an impact with the Earth in 2052. In any case, new data reveals, and this is how the different clones with the uncertainty, the global uncertainty of the data, and how this probability has been decreasing over time. Right now, the Earth is completely out of the path, but the Moon still has about a 4% of probability of impact. So we can get a new crater on the Moon of probably more than 1 kilometer in diameter in 2032. So if this happens, still the probability is small, but if such a thing happen, could be really an amazing example for future generations of why we need to invest in space telescopes and study these minor bodies of the solar system. And then we come with this amazing LSST survey operations in the Vera Rubin Observatory that are in fact a revolution in the discovery of hundreds of asteroids every night. We can see how this is happening. We need to take into account that the Vera Rubin Observatory is using different filters. Here, very exemplified, very simplistic. We see the red, green, blue of the different filters. So making continuous imaging in different filters of the night sky, everything that is not static, is a star very far away, then will become a track in the images. And we can see different tracks, red, green, blue. Red, green, blue, because this is what is automatically doing with this system of multi-filters to get these color images so amazing. So, of course, we can use any one of these images to get very precise astrometry that is made over the stellar background. We measure the location of each one of these hot pixels of the tiny asteroids. Over time, we can see each one is taken at a specific time, and then we get a really small, tiny arc of the movement of the asteroid. Remember, Vera Rubin Observatory is taking the entire sky at this resolution almost every 3 days. So he will be back. So this asteroid perhaps is not here, but will be over here. No matter there is a galaxy, we will find the track. And then we can get a larger arc of observations. On the other side, we will have really travel to get this capacity with other instrumentation. We can use very big observatories, but remember that most of these detections are on asteroids that are 25, 24 magnitude. So will be needed a really big telescope. So at least with these tracks, these arcs of observations, we can get an orbit. We can estimate the probability of impact with the Earth, and then decide if we need to invest more time, observation time, of largest instruments. But of course, this will be the starting point, and we really need this kind of observatory also over the Northern Hemisphere, because this is really making a fascinating monitoring of the southern sky, but we still need over the north. And this is how I will try later on at the end to put the video, this video that exemplified, but you can see the video already in the Rubin Observatory initiative. And this is one, the big challenge of all this is that we, as you know, from the video, more or less, the Vera Rubin Observatory has been discovering about 1,000 asteroids every night. So this is a challenge, but there is a very well-defined team that has already incorporated some of these May 24 detections into the main Minor Planet Center database. And this is the first asteroid. This is the name of the asteroid, 2025 MB18, that we can get the entire orbital elements with the uncertainty. This is the trajectory. This is Earth at the instant of observation, and this is the small arc will be more or less this size. This is the orbit obtained from the observation. So this is amazing science that can be done using the Vera Rubin Observatory. But remember that in particular, the Planetary Defense Office of the European Space Agency has been made big progress in the development of this extremely fast robotic telescope that is called FlyEye, and that in fact the first prototype is already operational and has been obtaining tracking of different really fast asteroids in close approaches from Matera, from Italy. And will be soon other instruments like this in different observatories around Europe. As I announced at the very beginning, the Joan Oró Robotic Telescope, operated by Monsec, Institut d'Estudis Espacials de Catalonia, has been already contributing for more than 1 decade in the follow-up of potentially hazardous asteroids. We went incorporated into the International Asteroid Warning Network, and now with the addition of a new telescope track, we expect to contribute to increase the study of minor bodies in the solar system. The implications for our future planetary defense strategies, of course, with Vera Rubin Observatory, we will discover millions of new asteroids per year. So opening a new age in which we will be able to track them and produce in advance much reliable impact alerts. In particular, in the case of close encounters with high probability of impact, we could implement palliative efforts like the one exemplified by that NASA kinetic deflection mission. And of course, we have also online a very nice way to popularize this field and to explain to the public how this is made. The new software Adam, developed by the Asteroid Institute, B612, remember the Little Prince book? This is the name of the asteroid, has been used by the Asteroid Institute to popularize this area. And this software allows us to introduce the orbital elements of a body, and online, you can do by yourself, you can estimate the probability of impact with the Earth in the future. So it's absolutely amazing. This is thanks to the Asteroid Institute. And of course, this is a big thing. If we are able to keep developing monitoring efforts from space, we could be relatively well protected from asteroids and comet impact hazard. Because the most important thing is to discover all these bodies in time. If we have years in advance before the close encounter with the Earth, then it will be much easier to implement a palliative effort like DART mission. Because DART was in situ demonstration that we are able to impact a rubble pile, an extraordinary difficult chunks of rock, big thing, like going to the Pyrenees and then pick up billions of rocks as with different shapes and bring to the space in a bag, 160 meters back, and then take it back. And then you will get an asteroid like this. As you imagine, it's a big challenge to be without a direct experiment. Try to know what would be the outcome of a collision with that, with a kinetic impactor mission. But we are able to deflect asteroids that are hundreds of meters in diameter, as this DART mission exemplified. And the effects of DART will be studied by this bright new mission of the European Space Agency, ERA, that will perform a very detailed post-impact survey of the effects on Dimorphos, this satellite of Didymos, of this DART impact. And for the very first time, we'll be also releasing CubeSats, some of the CubeSats touching the surface of Dimorphos, and then providing very important information about the nature of the body, the internal structure, thanks to the radio experiment that is going to bring through the body these signals. And then thanks to this, we will get very precise data on Didymos asteroid system. And we have a powerful reason to pursue in the study of asteroids. And the closest example was Tunguska. That was an airburst from a comet or asteroid. We don't know sure. We think that perhaps it was a fragment of comet Encke, but the accuracy of the trajectory of the orbit was not good enough to be completely sure about that. In any case, it was a rubble pile that is wrapped in the atmosphere on June 13, like today, 1908, with an impact energy release in the atmosphere of 10 megatons of TNT. So, and again, we were lucky. In the history of the humanity, it seems that so far we escaped of these events. But for 6 hours, more or less, this could have been produced over St. Petersburg. So could be perhaps changing our idea of the hazard from asteroids. And that's why we need to really study all these asteroid events. This is where the bolide was falling. This is the difference with St. Petersburg, was almost in the same track. And then here was the example obtained by Leonid Kulik, that was a pioneer in the study of Tunguska. Remember, 1908 was happening the event, and 19 years after the event reached ground zero, and they discovered devastation over 2,200 kilometers square of the taiga. Just the shock wave was completely collapsing the trees, and then the fireball was later on. Remember, a fireball like this from a comet, from an asteroid, will be dominated by oxygen, hot vapor, not plasma. It's not at the temperature we call usually plasma. Will be a temperature of several thousands degrees, just reaching the ground, and then with the amount of silicates that can be ablated in this phase of the luminous bolide, obviously in an atmosphere that is already 20% molar in oxygen, you increase the amount of oxygen. This is like a fire. Everything went incinerated in this process. So after the shock, just wait for some hot event. And still, we are contemplating, and just finishing with this, but quite naive in our understanding of the hazard produced by impact and asteroid events. We know a little bit about the circumstances in which impact craters are excavated over the moon. For example, we expect total destruction, vaporization near the impact crater. The devastated area could be 50 times the asteroid diameter in general. In the case of an impact on the ocean, can be produced as tsunami and energy transport falling again on the sea. But apparently, new studies suggest that the tsunami produced by unique impact on the ocean surface is not so powerful like the tsunami produced from the bottom of the ocean when we have a quake. It's highly more efficient, the transport of energy because this is in fact more one unique event, and the propagation of the energy in the ocean seems to be less efficient. And of course, the consequences over time, over weeks, months, years, in the global darkening can produce the fast climatic change we expect happen with the epoch of the dinosaurs, with clear consequences on agriculture, livestock farming, fishing on a global scale. And of course, the fires due to the oxygen injection and incandescent materials will be all nearby the impact, changing at high temperature the surrounding area. And of course, we still have not completely view of the poisoning of the biosphere by particularly sulfur, sodium, chlorine, phosphorus, because remember that small bodies are undifferentiated. So you can find in them, in different proportions, the entire periodic table. So when all these materials are released in a hot vapor phase, then you can have direct interaction with the atmosphere, and the consequences could be sulfates, nitric acid, destruction of the ozone layer, and many other that are not the point to develop here. And of course, the impact associated earthquakes. So really, we don't want to have an impact. We need to renovate the efforts to avoid this process. And this is the almost the last slide, in which you see here the probability, the impact probability of large impacts in the future. A body like 1 kilometer in diameter to be expected for the next 20, 30, 40 millions of years. So in general, we need to take account these small asteroids, which the frequency of impact is of centuries or thousands of years, and in fact are the most easy types of events that we can avoid with the right conditions. And everything that I explained here was already presented in some of these books. In Springer, I published Asteroid in Paris, that was translated to Catalan and Spanish by the University of Barcelona. And hopefully many other languages will come. But in general, I will just say thank you and do look up, because watching the sky and protecting the dark sky, we can get a direct link with our cosmic origin, but also we can get protected from these crazy worlds that are surrounding us. Thank you.
Thank you. Do you have questions?
Thanks, Jean-Maria. At the discovery rate that you expect from the LSST, I guess you're going to reach completeness for quite a number of asteroids and sizes and distances. So what do you expect in that domain in terms of having a complete sense of these asteroids?
Well, we expect, for example, to increase the number of asteroids of small sizes. In particular, for example, we have the evidence of collisions against the moon, that the flux over the moon is dominated by carbonaceous projectiles. So I will expect that the reason for we are missing many of these meter-sized bodies is because they are extremely dark projectiles. Carbonaceous in nature could be fragments of carbon-rich asteroids or comets, like this meteor-sized meteoroid we imagined in bolide phase last year, that coming from a Jupiter family comet. That is an example. Of course, this will have implications in the number of Jupiter family comets discovered. We are not only discovering asteroids, will be other populations of bodies, Trojans as well, Kuiper belt objects. And I think it's particularly important that for the very first time, we will get a really good statistics about the number of interplanetary visitors. Those small bodies like the asteroid Oumuamua or comet Borisov that are coming from other planetary systems and are crossing the solar system. So far, we were really bad in detecting them. We only detect in entire history, and thanks to the CCD cameras, we were able to detect these two bodies. But in the future, I think with this kind of global observation of the entire sky, we will be able to track many more and get some reasonable, reliable statistics about the numbers and the probability of impact. No? And they are specific missions, waiting for the next interplanetary interstellar visitor. Then interstellar objects will be one of the fields in which we expect a very significant contribution of the LSST.
More questions?
I have a question regarding this recorded last year. I understood correctly from our little talk we had a few months ago. The samples that I provide you do not fit your conclusions that it's a comet that comes within the Jupiter in orbit. So how would you explain those samples? Or how sure are you about that is a comet with that trajectory? That characteristics. What's the margin of error?
Well, in principle, we use a dynamic projection of the orbit. We studied the evolution of the orbit in the past, and we compared with the different programs we have to, according to the orbit, get a prediction of the type, the origin, family from which the dynamic family from which this object is coming, and this gives us that we are reasonably convinced that it was coming from a Jupiter family comet. So far, we are right now studying if some glasses that we recover in Portugal, thanks to you and your team, if it can be related. It seems that from the point of view of cosmochemistry, there is not a direct link, unfortunately. But perhaps there is some physical explanation that we are trying to figure out. And because the effects of a larval of this magnitude penetrating in the atmosphere, it comes, with a shock propagation in which perhaps was able to produce gases in the upper atmosphere, but due to the compression of the Earth's atmosphere, not directly the incorporation of materials of this comet, because we already analyzed this at Carnegie Institution, and there is not any clue that this is extraterrestrial. Probably the amount of material of the body is almost nothing, and is more related with the shock expansion of the ultraviolet in the atmosphere, affecting the Earth atmosphere materials. But still need to figure out. And we are looking, we are pursuing this thing, because is of great interest also for us. And it's quite unique. In my entire life, I was waiting for something like that, having a comet crossing, and a comet that is not in the size to be dangerous and can get very interesting clues about how comets disrupt in the atmosphere of the Earth.
Okay, let's keep it at this. I think pizza is already down. So thank you again, everybody.
Yeah. Okay.
Yeah, sì, certainly no,